Hello everyone, we will revisit the different factors which affect the tensile results once again, because now what we will try? We will try to solve few numericals which are practical in sense, okay? And how the different factors affect the tensile results, that we will try to see, try to understand by practical example. Okay. Now, the factors which we have discussed earlier was first the specimen length. Specimen length which directly affect the tensile result. For the same yarn, if we increase the specimen length, the tensile result, tensile strength, apparent tensile strength remains, actually becomes lower, that we have seen. So, basic thing is that it is a weak link theory that we have discussed earlier. The yarn, any material, as a matter of fact, breaks actually at its weakest point. Okay. So, that if we keep on increasing the test length, that the weakest point it will reach, okay. At certain weakest point it will break. Now, suppose in this figure the yarn length is say S 1 plus S 2 plus S 3 plus S 4, that is the yarn length, L 1 plus L 2 plus L 3 plus L 4 is the length of the yarn, and the breaking strength of the yarn with L 1 portion, it is S 1, L 2 portion S 2, L 3 S 4, L 3 S 3 and L 4 with the S 4. Okay. Now, if we see the S 3 is the least, followed by S 1, then S 4 and S 2, S 2 is the highest. Now, if we take the yarn length, total yarn length, it will show a result of breaking strength as S 3, which is least. Now, if we keep on reducing, then the mean value, if we say total yarn we break in 4 different tests, L 1, L 2, L 3, L 4 section of same length, we are just breaking into 4, dividing into 4 different sections. In that case, the yarn strength will be S 1 plus S 2 plus S 3 plus S 4 divided by 4, it is a mean, which is anyway it is more than S 3. That shows that the reduction in test length increases the apparent strength of yarn. Okay. Now, this, if we see that this is the if we in this example S 1 plus S 2, the 2 segments if we take, then the mean value, if we take the S 1 first portion as a result S 1 and second portion as a result S 2, then mean will be S 1 plus S 2 by 2, okay, that is mean. But if we take the total length of yarn, then the yarn strength will be S 1, which is basically less than the mean yarn strength with the 2 segments O double dash and O double dash O dash. So, these 2 segments if we take, then it will be higher. So, that is it shows S 1 plus S 2 by 2 is always higher than S 1. Now, in that way if we think that we total yarn, if we reduce the length with a smaller segment, in that case then the mean strength will always consistently will increase. Now, if we take this effect is known as the weak link effect, and also in addition to the length, the more the irregularity of the yarn, the higher will be the effect. Okay. So, that at higher irregularity, this weak link effect will be more. Okay. Hence, by adjusting the gauge length, the test result may be actually varied. You can change the test result of a particular yarn by changing the gauge length. Okay. So, it is important to specify the standard gauge length. Okay. It is important. Now, this is the, in this picture we can see that more irregular the yarn, so red color is the highly irregular yarn. In that case, that weaker point, more and more weaker point will be there. Okay. On the other hand, the blue color shows the almost regular yarn, although maybe the mean strength is lower than the irregular yarn, but in that case if we see its breaking strength, breaking point will be higher than the irregular yarn. Okay. So, for processing point of view, slightly lower average strength is okay with, but the yarn regularity should be better. Now, this Peirce empirical equation which shows that this R ratio R means the number of times it increases. Okay. So, that SL is the length with the L gauge length and SRL is the strength, mean strength with the RL gauge length. So, R times of L is that means that time it increases, and V is the CV percent of the yarn. Now, if we see, if we increase the R, that means that the yarn strength, mean strength will reduce, and also at the same time if we the V CV percent, if it increases, the strength will be lower. Now, see R, if R increases, the ratio SRL by L, that means RL is the longer length, strength with the higher length, the R times of L length. So, suppose it is a, if we test its gauge length is a 10 centimeter, and if R is say 5, that means for if we test 50 with a 50 gauge length, it will be that we can just check that how many time it will reduce, okay, the strength. And similarly, the higher the irregularity, the V is the CV percent of the strength, higher the irregularity will show lower the value of SRL by SL. So, that means the if we take the irregular yarn, the same length gauge, keeping the same gauge length, if we take the irregular yarn, in that case it will be totally, it will higher irregularity, the strength will drop. But in this equation it shows the, if we keep the gauge length same, in that case the effect of CV we cannot see from this equation, because in that case R will be 1 if we take the same gauge length, only changing the variability. In that situation this equation is not valid, because R will be 1, then total this segment will be 0, okay. Then it will be same, it shows same. In that case impact of the yarn irregularity is not there. So, yarn irregularity impact will only come if we change the gauge length. So, according to this equation, okay. And rate of loading or time to break. So, in that case most textile materials show an increase in breaking strength with the increase in rate of extension, that we have discussed already. This is mainly due to the viscoelastic nature of the material, and it has got two components, viscous component and elastic component. In the elastic component, actually in the elastic component it is shown by the spring model. So, we can see here. So, any textile material we can represent with a spring and viscous model, okay. So, that this is the viscous model. In that way we can show here this spring section, it is basically it changes with the extension, load changes with the extension, but this viscous segment the load changes with the rate of extension. So, if we increase the rate of extension, in that case the load, actually the strength, the material will increase. Now, you can see here this is the spring model and this is a dashpot model, okay. So, viscous model, and here if we apply force, the force has been divided into two components, F1 which is by spring and F2 by dashpot, spring dashpot model, and the F1 increases proportionally with the that is the extension. Okay. That is a this is proportional as the extension increases it f also increases, f1 also increases, but in dashpot the f2 increases with the rate of extension. Okay. And also we have seen as we increase the rate of extension the stress exerted by the material increases. Okay. So, for at high rate of extension, this is the nature of curve which is shown by the green line, and at low rate of extension it is a blue line. Now, based on this basic understanding, now we will try to solve few numericals. Okay. Now, before that, the rate of loading and time to break, this formula we have already discussed, where the F t is the load exerted by the material trace or load exerted by the material when the breaking time is t, and F 10 is the for breaking time 10. So, this is the general equation. If we just rearrange the equation, we will reach to the it is a general standard equation F t minus F s by F s equal to 0.1 log its base 10 with s by t, where t is the breaking time for any force at the breaking time t, s is the breaking load at the breaking time s, and s is the time. Okay. So, that from this using this equation we can solve different practical problem. Okay. Now, try to see the problem. So, the standard time to break a specimen as per the BS standard, it is a 20 plus minus 3. So, we have to decide, we have to select the strain rate in such a fashion the standard time S is typically it is a 20 second. Okay. Accordingly, we can decide. Now, this is the problem. If a yarn shows a strength of 400 centinewton when the time taken to break was for 10 second. Okay. That is this we have discussed earlier also. So, at 10 second time to break, the strength is 400 centinewton. Calculate the breaking load if the rate of loading was increased to cause the yarn to break in 1 second. So, we have increased the breaking load, that means breaking rate. The rate of extension we have increased, that means here the viscous, the dashpot it is coming into picture. So, in that case if we increase the rate, so this is the formula we have seen earlier equation. So, F t is the breaking load for a material to time to break of t second, and F 10 is the breaking load for a time to break 10 second. This is the, and here 10 second, F 10 is the 10 second, at 10 second F 10, this F 10 becomes 400 centinewton, it is given. Now, what we want F 1 we want. Okay. Now, F 1 equal to F 10 multiplied by 1.1, this 1.1 minus 0.1 log 1 log t, okay, log 1, this is the, and that gives log 1, it gives 0. So, it becomes 1.1 multiplied by 4. So, 440 centinewton. So, here it shows we can see as we increase the rate of extension by 10 times, the load breaking load increases by 10%. So, that is the thing, but it is not the in general formula. 10 times increase in breaking extension, rate of extension increases the 10% of breaking strength. Okay. From 400 it becomes 440. Now, next numerical we can see. Now, if the rate of extension of a yarn is doubled, so we have made the rate of extension, we have changed it in such a fashion, rate of extension has become doubled. Okay. What will be the percentage change, percentage increase in measured yarn strength for the same gauge length? So, what we are doing here we are not changing the gauge length. So, the problem is like this is yarn, this is moving jaw, okay, moving jaw. This gauge length we are not changing. Okay. At certain this gauge length, suppose speed was v. So, rate of extension was v. Now, here next time what we are doing, next sample we are keeping the gauge length same gauge length, but we are giving 2 v 1. This is the second condition, and here what we have given, and what we are trying to know that the rate of extension is double. So, it is the rate of extension we are increasing. So, what will be the percentage change in percentage increase? Definitely it will increase in strength, breaking strength, that we are trying to understand. Now, so here condition is that breaking elongation remains same. Okay. So, we are not changing the breaking elongation, but we want to know the breaking strength. So, in first stage the time to break is S, okay, and in second stage time to break is T. So, as we have doubled the speed, so time to break, because your breaking extension remains same. So, time to break will be halved, it will be half of the early S by 2, it is a time to break. So, S and then T equal to S by 2. So, using the earlier formula. So, this is the formula here, S by T. So, S by T becomes 2. So, this is the F T minus F S by F S, and percentage change in breaking strength or percentage increase in breaking strength means F T minus F S by F S multiplied by 100, that is what we want to measure. F T minus F S by F S multiplied by 100. So, if we multiply this right hand side 0.1 log S by T, that will give us the percentage change in the yarn strength. Okay. So, that is the way we have to do. So, this 0.1 log S by T multiplied by 100, this is percentage change, and S by T as from our condition it is 2. Okay. S by T it become 2. So, 0.1 log 2 multiplied by 100, that is the percentage change in breaking strength, and it is coming out to be 3%, 3.01%. So, that is the problem. So, we can keeping the breaking elongation, suppose in this by changing, when we are changing the breaking rate, okay, rate of extension, considering the breaking elongation is not changed. Okay. In that case, if we double the rate, and the percentage change in strength will be say 3.01%, that is the thing. Now, if we know the breaking extension, then also we can solve the problem in the same fashion. So, if we know the breaking elongation for both the cases, in that case we can calculate, we have to first calculate the time to break. So, in first stage and time to break in the second stage, in that, and then we can do. So, in different way we can solve the problem. Okay. Next problem is that this problem we have to understand, this is it is a very practical problem, and it is a this type of problem we can actually we study in research. Okay. Now, a 40 NE 6733 polyester cotton blended yarn showed a breaking load of 300 gram when tested in CRE constant rate of elongation tester with 100 millimeter gauge length and 100 millimeter per minute traverse rate. So, effectively this 40 NE and 6733 in this numerical, in this problem does not mean anything. Okay. This is an yarn. Okay. One should not get confused, because this is the just a specification of yarn. Here we are trying to understand the effect of rate of loading and time to break. Okay. The situation is that here the problem here is that the condition here in first case our breaking load 300 gram with what condition 100 millimeter gauge length and 100 millimeter per minute speed. Now, what we have seen earlier, both this gauge length and speed they have effect. Okay. If we increase the gauge length, then the breaking load, if we increase the gauge length, breaking load reduces. Okay. That we have seen, and if we increase the traverse rate increases, then breaking load increases. So, that we have seen here. Now, what we are doing here, that initially that the speed was the 100 millimeter per minute and gauge length was 100 millimeter. Now, what are the expected percentage change in observed tenacity of the yarn if the traverse length is increased to 500 millimeter per minute. So, from 100 to 500 millimeter per minute we are trying to do. Okay. From 100 to 500 millimeter per minute we are trying, and we want to. So, if we increase the traverse rate, definitely there will be increase in this breaking load, and also from 100 and this is one, and situation 2 is from 100 millimeter gauge length we are making it to 500 millimeter gauge length. And now we want to know the percentage decrease in the strength, breaking strength percentage decrease here in this case. Okay. So, situation 1 is that traverse length is increased to 500 millimeter, keeping the gauge length is constant. So, it is from 100 millimeter per minute to 500 millimeter per minute we are doing, keeping the gauge length constant, and in next case it is a gauge length is increased to 500 millimeter, keeping the traverse length rate constant. Okay. And the assumption is here that assuming a constant breaking extension of 25% in both the cases, in all the cases, initially percent after changing the gauge length, after changing the rate. So, always in every situation the breaking extension remain 25%, we are not changing it to make it simple, and single yarn strength CV remains 10% for all the above conditions. There are 3 conditions. So, this if we change this thing, that also it will be very simple, because we have to get the data. Here it is 25% is giving, that means there is no change in the breaking extension. Now, solution is that, so we know this this is the formula for, actually if this formula will be used when we change the rate of extension. So, rate of extension, keeping the breaking extension percent same, if we increase the rate of extension, that means time to break will be reduced. So, that is how we will calculate here. So, as the traverse rate in first condition, as the traverse rate is increased by 5 times. So, from 100 to 500 we are making, the time required to break is reduced by 5 times. That is the straightforward situation, because our breaking extension is same. So, in that situation it is becoming very simple, but if we know the breaking extension, that also we can calculate. If we know the with the gauge length we can always calculate, but it is a simple. So, that S by T ratio is 5. Okay. S is 5 times of T. Okay. So, S is 5 times of T. So, S by T becomes 5, then the things are simple. So, 0.1 log 5 multiplied by 100, that is the percentage increase in strength. Okay. So, if we see again S by T is 5. So, percentage change here we can definitely say it is an increase. Okay. So, percentage increase in observed tenacity, it is basically f minus f t minus f s by f s multiplied by 100, 0.1 log s by t. So, 0.1 log 5 multiplied by 100. So, it becomes 7%. So, from 100 millimeter per minute to say 500 millimeter per minute, keeping everything constant. So, we will get a result apparent increase in strength of a yarn by 7%. So, that we cannot do because we have to follow a standard method, but for research purpose one must know and how to calculate this extent, that is observed result, and how to get the predicted result. One has to do this type of numerical. So, one can predict if we increase the rate of extension, what will be my increase in strength, percentage increase in strength. This is actually important in many technical application where suddenly increase in breaking stress or rate of stress is rate of extension is very high. In that impact, say like in impact type of condition. So, we can predict the percentage increase in strength. Okay. Next is that situation 2, that gauge length is increased by 5 times. So, we will use another equation, this is the equation here. So, 1 minus S R L by S L equal to 4.2 multiplied by 1 minus R to the power minus 1.5 multiplied by C V percent and by 10 100. Okay. So, here R means what is the how many times the gauge length has increased, 5 times it has increased, it is a 5. Okay. And which one is unknown here? The V is unknown, but V is given. So, in the numerical the V value is given, that is a single yarn strength C V, it is a 10 value it is given. So, we will use V as 10 here. So, V is C V percent 10 is given. So, V is 10. So, we will simply use this formula, and this is nothing but if you multiply this with 100, it is nothing but percentage change in strength, because S L minus S R L by S L, and this 100 will come in the left hand side. Simply it will go give us the direct value of percentage increase in decrease in strength. X L is more than S R L definitely. So, in that case we can directly calculate. So, the percentage change here it will be decrease, because S R L is less than S L, percent decrease in observed tenacity will be S L minus S R L by S R L multiplied by 100. This 100 will come to the left hand side, then 4.2 1 minus 5 to the power minus 1/5 multiplied by 10. This 10 is the C V percentage, and if we get this value, this will come out to be 11.56%. That means, if we change the gauge length 5 times, our expected decrease in strength will be 11.5%. That is the basic. Now, whatever problem, whatever data are given, so we must be able to calculate the expected change in strength. Okay. And then we will now see, we have also seen this pendulum lever principle instrument. Now, we will see one numerical, what will be the time to break, that we will try to calculate. The principle, let us just revisit once again. This is the pendulum, okay. This one is the pendulum with a, this is bob, which a certain mass is there, and this pendulum principle is it's a ring is there, it's a pulley, it's a fixed, this pendulum is fixed with this pulley, it's a single unit. This is the single unit, as we can see here. This is the bob of pendulum, certain mass. This is exactly same single unit. Okay. It is a rigidly fixed here, it is nothing. Now, if we and it is a fulcrum at the center, this is the center. Now, if we pull by some rope, inextensible rope or metal strip fixed somewhere here, if we will pull and it is the center, this will try to rotate. Suppose this, if we try to pull in the downward side, this will rotate anti-clockwise. So, this will get deflected, this portion will get, this will rotate anti-clockwise, this will get deflected at certain angle. This we have already seen in last class, and also we have seen how to calculate all the different parameters like the machine rate of loading and time rate of loading. Okay. Here for extensible material, this is the bottom jaw. Okay. Bottom jaw moves at a constant speed v, and top jaw moves, but it is not at constant speed, it depends on the extensibility of the material between jaw J1 and J2, and the movement of this J1, movement of J1 actually gets signal, gives signal to the load measuring arrangement. It basically excites the load measuring arrangement and it deflects, and we have seen the calculation. So, there are two types of parameters here. One is called machine rate of loading, it is denoted by mu, that is increase in the load, increase in load per unit increase in the displacement of the upper jaw, that we must remember. Here what is the load increase here, with the increase in load per unit deflection, unit movement of the upper jaw, that means df by r d theta. Theta is this angle of deflection of this ring of this pulley, and that r is the radius of this pulley. So, df by r d theta, which is nothing but the machine rate of loading, and that is proportional to the cos theta. That means, at the starting point it is a maximum, and gradually it reduces, the machine rate of loading reduces with the deflection. Similarly, that this at the start and at the 45-degree deflection, it is the ratio is 1:0.707, that is the ratio of cos theta. Okay. And standard machine rate of loading means this constant part is the standard machine rate of loading, and that is denoted by the mu 0. Okay. So, standard machine rate of loading, the unit will be the, it is a say Newton per centimeter. Okay. This is the force per centimeter. So, Newton per centimeter, that is force per any displacement, that is the unit of the standard machine rate of loading. So, if one asks the what is the unit of standard machine rate of loading, that is the say centinewton per centimeter, any similar unit should be there. Another term is that it is called time rate of loading, that is a rate at which the load on the specimen increases, that we have seen the derivation, and it is nothing but the mu multiplied by v. So, if we multiply the machine rate of loading with velocity of the bottom jaw, then we will reach the time rate of loading, that we have seen. Now, we will see. So, it is again it is proportional to the cos theta, and maximum at 0 and minimum at 90-degree deflection. Now, we will see, we will try to solve one numerical here. The following are the tensile test data of a 30 Newton, 30 NE, 30 English count single yarn, single basically cotton yarn, while testing on tensile tester. So, we are this is the single yarn is tested in a pendulum type tensile tester, works on a pendulum lever principle with standard machine rate of loading. It is given mu 0, it is 440 centinewton per centimeter. So, that is the standard machine rate of loading which is given here, and the tenacity breaking tenacity of the yarn. Tenacity of the yarn is given 11 centinewton per tex and breaking extension is given 7%, 7% breaking extension, and gauge length is given. So, gauge length is 20 centimeter, that means the distance between upper jaw and lower jaw, and traverse rate is given 57 millimeter per minute. Calculate the time to break. So, we have to calculate now time to break. Now, so if we see the picture here, so this traverse rate, which one should we take? Should we take the top jaw or bottom jaw? It is basically bottom jaw. Top jaw is the, although it moves, but it is not driving, driver is the bottom jaw. So, it moves at a constant speed v, okay, and breaking extension is of the yarn is given. So, we can calculate the total extension, because our gauge length is known, gauge length is 20 centimeter. So, 7% of 20 centimeter is the total extension. So, 1.4 centimeter is the total extension of yarn before it breaks. Okay. From there we can calculate. Now, 30 Newton, it is 30 Ne is given, and here the tenacity is given in centinewton per tex. So, we must convert this 30 Newton 30 Ne to tex. So, it becomes 19.68. So, 590.5 divided by 30, it comes out to be 19.68 tex, and maximum breaking load. What is the maximum breaking load? The 100 is the tenacity. If we multiply with the tex, then it will get 216.5 centinewton. This is the breaking load P max. And also we know the mu 0. What is mu 0? Mu 0 is standard machine rate of loading. So, that is the constant standard breaking 440 centinewton per centimeter, and if we take the reciprocal, which is we can denote by m, that means 1 by 440 centinewton per centimeter by centinewton. This is the reciprocal of machine standard machine rate of loading. Then we can, if we multiply the reciprocal of standard machine rate of loading, which is 1 by 440 centimeter per centimeter with P max. What does it mean? Here this top jaw means it gives the standard machine rate of loading, because per unit movement of the top jaw, the rate of loading, the loading per unit movement. So, per unit movement it is the m, and if we multiply by P max, that means it will give us the total movement of the upper jaw. Okay. So, m multiplied by P max, it is coming out to be centimeter. So, 216.5 divided by 440, it will become the total movement of the upper jaw, and velocity of lower jaw is known, it is a 57 millimeter per minute. So, in this way we can calculate. So, total movement of the upper jaw is 216.5 by 440 centimeter. This is the total movement of the jaw 1, J1. Okay. And E is the extension of yarn, that we know extension of yarn, it is a 7% of 20, that means 1.5 centimeter. So, this is the total movement of upper jaw, and extends during this process, extension of material is 1.5 centimeter. Now, what is the total movement of bottom jaw? Then if we add this m P max plus E, it gives the total movement of the bottom jaw. So, total movement of the lower jaw J2 will be m multiplied by P max, this is the movement of upper jaw, plus extension of the material, that is total movement of the bottom jaw is we can calculate. And then velocity of the lower jaw is known, we know the velocity of the lower jaw 5.7 centimeter per minute, and then we can calculate everything, we can calculate the time to break. So, total time to break is m P max plus E bracket whole bracket divided by V. So, you just replace this data to 16.5 divided by 440, that means m and then plus E, this is the value m p max. What is the m p max? Is the 216.5 by 440 plus E value, E is 1.4 and divided by 5.7 centimeter per minute. So, this will give us the total time to break in minute. So, this time is coming out to be approximately 20 seconds. So, this if we know, if we can practice this type of numerical, then our total principle of this instrument will be very clear. Okay. So, this is giving us the value 20 seconds. Okay. So, we will continue with this. Now, we have discussed different test instruments earlier. So, we have discussed the different principles like inclined plane principle, or we have discussed the stellometer, we have discussed Presley strain tester, and we will now discuss the strain gauge principle. In last class we have started this principle. So, strain gauge principle, it gives idea about that it is the basically most of the modern instrument it works in this principle. Here the advantage is that this is the instrument where it works in CRE principle, okay, constant rate of elongation principle, because the deflection of the upper jaw here it is negligible, we can neglect as compared to the movement of the lower jaw. Most of the modern tensile testers work on this principle. When the beam bends, the length of the upper face, that is AB, gets extended, CD gets contracted and NL remains unchanged. Okay. So, in that case that we have discussed, that we can actually fix some resistance where here. So, then how to convert this value, the change in resistance, we have seen that we can two resistance where we can put in the upper surface and two in the bottom surface. So, that upper surface get extended and the bottom surface get contracted. So, accordingly this resistance changed. So, then we can form a Wheatstone bridge. Okay. From there, so two resistance wires are placed on the upper surface and other two are on the lower surface, and it forms Wheatstone bridge. Now, in normal case what happen, when the things are balanced, there is no load with the beam undeflected, okay, no voltage across CD. So, there is no voltage across this. When a voltage is applied across the AB, so across AB if we input voltage, so across output there is no voltage because it is a balanced. But when it is deflected, the values of this resistance resistor will get changed. So, the deflection occurs and the value of the resistance changes and the voltage is produced across CD. This voltage, output voltage, it is actually proportional to the applied load. Okay. That means, the deflection, although it is negligible, but due to that deflection the resistance changes. The minute change in resistance we can actually record in the form of voltage. Okay. That electrical signal we can get, but mechanically deflection it is negligible. So, the advantage is that it is free from inertia that we have seen earlier instruments like say pendulum. It is actually its problem is its inertia problem is there. So, in pendulum if we see, suppose this is the material, this is jaw 1 and this is jaw 2. Once it started, so that means the extension is taking place, and what this deflection is also taking place here, but due to the initial inertia of this heavy load, it will not move immediately. That inertia effect gives us wrong result initially. Okay. And this is actually true for other instruments, but here the inertia effect is not there. So, this is the advantage of this instrument. The deflection of the end of beam is very small. So, that physical deflection is very small mechanically, that is why we can assume it is almost 0. So, we can see that we can tell it is the condition, it is a CRE principle. This is the one of the rare instrument which works in CRE principle, otherwise CRE mechanism is very difficult, because it actually you cannot measure the force. We can get the CRE, but we cannot measure the force, because force we have to measure from the other side. So, other sides, like this is the fixed jaw, this is the movable jaw. Movable jaw it moves, we can move it at constant rate. So, okay, but the load has to be measured in other direction. So, in earlier case we have seen in pendulum case, here load is, we can get load by movement, direct movement of this upper jaw. If it does not move, then will the load actuating load measurement system will not work. Okay. But here as it is moving, the load has to be measured here without any deflection, and that is why this strain gauge principle here, if we assume that there is no change in movement in upper jaw, then only we can get, but the confusion comes here. The total actuation, total load measurement, it is basically the change in resistance, it is basically after deflection. If it does not deflect, then resistance will not change, but at the same time we are telling that there is, it is a CRE principle, because it is a very deflection is very small. Okay. That is very important, we have to understand this basic concept. And versatile instrument we can use for yarn, fiber, many instruments we can use for different types of wide range of material, we can use wide range of load, we can, so from few milligram to say few tons. So, that range we can have instrument, and main disadvantage is that it is a very sophisticated instrument. For any repairing we need expert technician, and basically chances of drift in the electronic circuit. So, that the Wheatstone bridge after repeated deflection, it may, the resistance may get changed. So, in that case we have to recalibrate once again. Okay. And high initial cost, obviously its cost is very high. Now, we will start another concept which is practical in nature, and it is more towards the application. See, if we test tensile strength in static condition, that may not be actually applicable in normal application. Okay. In normal running of yarn, the breakage occur in dynamic condition. So, static measurement only give us idea about its strength, but dynamic measurement will give us the practical applicability of the material, like its the method is called constant tension winding test. So, it will replicate the winding method, okay, and then give us the idea about the tension required for a particular breakage. So, it provides conditions somewhat similar to the actual processing of yarn during winding, warping, sizing. So, knowing only the yarn strength in static mode, it will not help, because that will give us the test value of very specific length. Okay. But yarn which is giving very high strength, that may fail, because if that yarn contains very frequent weak point, and this constant tension winding test gives idea about the number of breakage occurs, okay, for a particular at a tension, particular tension, that idea we will give, and this test is closer to actual running condition. Okay. So, this is this instrument, it is basically nothing but a winding machine, where this is a feed roller, this is take up roller, and this roller is just for putting load on the yarn. So, at certain load we would like to test, okay, at certain tension, and what we measure? We measure the number of breakage occurred per 1000 yard. So, that is the tension is the value. So, say at say T tension, number of breakage occurred say 10 breakage occurred. So, standard is that number of breakage occurred say 20 at what, that is the tension required to have 20 breaks per 1000 yard, that is the tension. If we get, if we do not get, if we get less than that, then we increase the tension. So, till we get 20 breaks per 1000 yard. So, that way this is, so here we can change the load. A, B are fixed pulleys and P is movable pulley, because of the depending on the extensibility of the material it may change. So, because we are putting load on that. So, under static condition the tension of the loop will be 0.5 L. So, 0.5 L means basically that the loop is there. So, L is the total load. So, that will get distributed. So, that under static condition it will be 0.5, it will equally be distributed, but under dynamic condition it will change. Okay. The tension imposed on the yarn will cause it to stretch. So, stretch, there is a tension. So, there will be stretch is E, then E is the stretch of the yarn during tension. That means, we have to adjust the speed of Vt and Vx accordingly. So, Vt will be higher than Vx, that we know, if we know the extensibility of the yarn, that we can adjust the Vt. Okay. So, this is, I think this will be reversed. So, Vt will be Vt equal to Vx multiplied by 1 plus E. Okay, that is the thing. Necessary means are required to adjust the input and output velocity, that we have to adjust. If we know the extensibility, we have, if we have some idea about the extensibility, then we have to change, because the extensibility is mainly due to the load, okay, that we have to adjust, otherwise the yarn will be slack. And the as I have mentioned, standard breakage rate is 8 breaks per 1000 yard of yarn. So, it is not 20 breaks we can also get, but it is a standard, as per BS standard it is a 8 breaks per 1000 yard of yarn. That means, in this instrument it is expressed in terms of load required for 8 breaks per 1000 yard in the yarn. So, we will continue with this topic. Till then, thank you.